thank you, Professor Friedman, for this enlightening information. And I heard Professor Friedman for many times, and I can tell you that each time he comes to stage, the discussion became more interesting. So hopefully in the rest of the day, we'll hear more of Professor Friedman and Professor Stilian to get more important information. I think the presentation and the lecture of Dr. Moti Bril is an excellent example of what the Nuclear Forum is doing. We get together and we discuss, sometime by Zoom, sometime physically, and everything is allowed to say. Even if you say the most peculiar or unrealistic thing, we can discuss, we can argue. And I think that dirty bomb, it's classical, but I can tell you it's definitely not the last. We have many topics like this that all over the world, all of the news, and unfortunately, authorities and governments are talking about things that if they ask the professionals, they'll see that it's like an empty balloon. So thank you, Dr. Moti Bril, for this enlightening information. And we have some questions for the audience, but please, I would like to go on, so we'll try to answer them later. We would like to go over one more thing. It's important also to say, I remember that, I don't know if people know, but mice, they can drink radioactive water. And mice, they can drink radioactive water and nothing happens to them. They just go with the flow. There's no other animal in life that found out to be. So there are many experiments made on mice, but just so you know, so if mice come to a territory with nuclear problem, he has no problem. So we have to learn something from the mice as well. We'd like to go over to India, to dear colleague, Dr. Sushil Gupta, former senior member of the Nuclear Power Corporation of India, Ltd, the Department of Atomic Energy, Government of India. He will talk about enormous amounts of nuclear disaster insurance. And I know for Dr. Gupta, like many others from this Congress, we know each other for a few years, but we never actually met physically, but we are really friends. We go in some committee together. And we all know that money talks. So Dr. Sushil Gupta will talk about how money is changing the world. If I take Fukushima or Chernobyl, they had an insurance, Fukushima, you know, we all understand that Japan is an advanced country, is a rich country, is very disciplined, very professional. And any parameter you check, Japan is a very high level in training and everything. And although that Fukushima incident had happened, they didn't know what to do, and I'm not pointing a finger at them, but we can do it at the same other countries. So, for example, the insurance was insured at $1 billion, and the damage was $450 billion. So today there are some solutions all over the world to do some funding, etc. So I would like to take the discussion to Dr. Sushil Gupta in India. Dr. Sushil, please take the floor.
Namaste. My name is Dr. Sushil Gupta from India. The topic of my today's discussion is immense amount nuclear disaster insurance. Next. The agenda of my presentation is why nuclear insurance. So, and then including past major nuclear accidents, insurance basic concepts such as insurance pool, nuclear pool coverage and basic requirements, type of coverage, coverage and duration, nuclear pool in different parts of the world, financial cost of nuclear pool, and with an example and conclusion. Why nuclear insurance? This is the first question which comes to my mind. So there had been several nuclear accidents worldwide. As we know, nuclear accidents are low probability, high risk events. The 1945 Hiroshima-Nagasaki bombing compelled the world to understand degree of nuclear risk, the need to generate electricity from nuclear power plants, which is clean, green, and safer, met with few major accidents such as Chernobyl, Fukushima, and 3 Mile Islands. The Chernobyl nuclear power plant accident it was the worst man-made nuclear disaster that resulted in core meltdown. It occurred on April 26, 1986, and it has happened due to operator errors, which caused a reactor explosion, releasing huge radioactive material into the atmosphere. So over 7 million people, including 3 million children, lived in contaminated areas. Over 5 million people still live in contaminated areas. Radioactive fallout affected a large area. You can see on the right figure the affected areas and radiation levels, and it has created so far over 25,000 fatalities. On the left, you can see the collapsed dome of the reactor building. The Fukushima nuclear power plant accident, it was a double whammy. First 9 magnitude Toku earthquake, which resulted in a 10-meter height tsunami at the Fukushima nuclear power plant site location. It occurred on March 11, 2011, and this event was much beyond the design basis of the nuclear power plant. For example, the tsunami height of 10 meters, while it has been built for a maximum tsunami height of 5.7 meters. It was also the worst nuclear disaster in Japan history, which resulted in failure of emergency power supplies to all the 6 boiling water reactors. At the time of the accident, Unit 1, 2, and 3 were operational, and Unit 4, 5, 6 were on outage. In fact, Unit 4 was not even having the fuel loaded in the reactor building. It has a combined capacity of 14,380 megawatt thermal energy. This is a world's 15th largest nuclear generating station. This combined earthquake plus tsunami, this double whammy, it created hydrogen explosions in Unit 1, 2, 3, and 4, which released the radioactivity to the environment to a significant amount. However, all the nuclear power plants in Japan has automatic seismic scrams, and that has worked in this case also because magnitude was very high. So it's shut down even Unit 1, 2, and 3, which were operational. But as you know, that seismic scram just doesn't completely stop the nuclear reactions. You know it very well. So it became subcritical in a very short time, but still you need cooling water to cool the reactor cores to remove the heat from which is happening due to the nuclear reactions. The economic losses were of the order of USD 360 billion as per some estimates, and it has also resulted for 25,000 fatalities. Japan country declared a state of nuclear emergency, and people completely evacuated in over 20-kilometer radius areas. Now coming on to some basic concepts about the insurance. The first term is, which comes is risk. Risk is nothing but uncertainty regarding financial losses. Insurance is a social device or instrument for dealing with risk. A reinsurance is insurance for insurance companies. Co-insurance is sharing one risk amongst multiple insurance companies. Policy is a contract that specifies what risks are covered and how much will be paid out for the losses. Premium is money paid to to purchase the policy. There are other 2 terms which is called pure premium or average annual loss. So in catastrophic modeling, average annual loss plus margins are called as a premium. Risk management for individuals as well as for companies. So for individuals, risk management can be done, for example, by retaining risk, because as you know, one cannot do anything about an aeroplane fall on your house or choose to ignore risk. For example, you don't buy earthquake insurance or fire insurance. You can avoid risk by don't having or buying a house in high seismicity prone area or in a high flood zone. Or you can reduce the risk by having your house which is seismically strong and having provisions like earthquake early warning systems. You can transfer the risk through insurance, of course, the financial risk. Insurance companies, they can spread their risk across geographies, for example, transferring the risk through risk transfer mechanism. They can also reduce the risk by underwriting guidelines, by giving discounts to houses or buildings or structures, which has, for example, seismic alarm, which also has smoke detectors, which has a base isolation. As you know, the law of large numbers is nothing but it is a, as you know, larger the number, you can more easily predict the future losses. Insurance company must predict the future losses on a group basis in order to arrive at fair premium for individual within the group. Insurance pool is a mechanism whereby a number of insurers through an association jointly underwrite a technically challenging type of risk. Pools are typically found when a risk is high in severity and low in frequency, such as the nuclear accident. Pools are further categorized by insufficient capacity, being attracted to a class of business. This may be from an individual insurance company, because that company may not have this risk appetite so big. So that's why several insurance companies join in a pool. Nuclear insurance pool associations of insurers who jointly insure a particular risk or class of business. Nuclear pools cover nuclear power plants and other nuclear facilities, such as research reactors and nuclear transport. The type of coverage for nuclear power plant, it could be on-site, that is material damage insurance. It could be off-site, legal obligations liability insurance. Coverage and durations. Earlier, the coverage duration for a nuclear pool was 10 years, which has now been extended to 30 years. So nuclear insurance pool in different parts of the world, there are several insurance pools worldwide that are active in different countries and geographies, and their list is given here. I can read a few. That Nuclear Risk Insurer Limited, this is from UK. Chase Nuclear Insurance Pool, this is from Chase Republic. Nordic Nuclear Insurers, the Finnish and Swedish merged in 2020. This is Finland and Sweden. Swiss Pool of the Insurers of Nuclear Risk. Switzerland, American Nuclear Insurance, US, like that. There are many more. And last but not least is Indian Nuclear Insurance Pool, which is from India. Financial cost of nuclear insurance pool. This is one example from US. The total pool in US is 13.46 billion. Owner of the nuclear power plant pays 450 million in private insurance. There are about 104 nuclear power plants in US. And if a nuclear accident surpasses this amount, then each plant pays up to USD 1.121 million into the second tier insurance, plus a 5% surcharge. In conclusion, I would say there had been several nuclear accidents worldwide. Nuclear accidents are low probability, high risk events. Nuclear insurance pool in help in mitigating financial risk of a nuclear disaster, risk transfer across geographies, and effective way to mitigate financial risk. And there is an immense amount in nuclear disaster insurance. Thank you for your time.
Thank you very much, Dr. Sushil Gupta. And we say the money talks. We do have some questions, but I would like to bring you up, Dr. Sushil Gupta. The question comes from Dubai, from Dr. Jabari Mahmoud, and he's asking the question I think many people ask: how this problem of the delta between the sum of money of the insurance, which is usually low, and what do the country does, which means if we take Chernobyl and Fukushima, as mentioned before, the money insured and the funded is quite low, and they need to bring a lot of money. So I will raise you in a minute. Dr. Sushil Gupta, please wait 1 second. So I think that the money problem is the money is showing the problem, because money is just a transformation of energy. So if we solve this problem of money, we can do how to do better things in the future. Do we have Dr. Sushil Gupta or not yet, please? Okay, Dr. Gupta, can you hear me, please?
Yes, I can hear you.
Okay, thank you very much for this fascinating presentation. Did you hear the question of Mr. Muhammad Jabari from Dubai? Dr. Sushil, did you hear the question? Okay, can you? Yes. Okay, please answer Mr. Muhammad Jabari.
Okay, the answer to his question is it's a very good question, and I would say very practical question, and I appreciate the question. The answer is it's a very small fraction of the total cost of the nuclear facility if you see in terms of insurance. So pool is a best way to mitigate the financial losses from a nuclear disaster. It is hardly of the order of 0.1 to say maximum 1% of the total facility cost. So it's a very low amount which can help in ensuring the nuclear facilities. When I say nuclear facility, there could be research reactors, including nuclear power plants, and even a transportation of nuclear material. All these are covered under nuclear insurance pools. And number of share of the insurance pools are more, lesser is the premium. That is another advantage. If 2-3 countries goes together to make insurance pool, that further reduces your premiums for the cost of the having nuclear insurance. Moreover, through nuclear insurance, in a way, you are transferring risks across geographies. For example, in Fukushima, if Fukushima has a primary insurance of Japan, has taken insurance of Fukushima nuclear power plant. But had it been only that insurer, it would have was the beyond capacity of that single insurer. So what insurer can do, it can transfer its risk across geographies through reinsurance. So there are reinsurance products. So insurance can go to reinsurance pools and they can join them. And so risk goes transferred from Japan to India to say US to Bermuda. There are a lot of reinsurance companies which can also take part.
Okay, can you give us 1 or 2 more examples of other incidents? Because we all know Fukushima and Chernobyl. Can you tell us from your experience? Because the audience doesn't know, but you are also advisor to the National Federal Bank of the world. So I know you have a lot of experience with this. Can you give us 1 or 2 more examples, more others than what we all know about?
One more is 3 Mile Island accident, which is quite big in size, and there are many more which are I would say a smaller accident, or which in a way just saved at the, I would say, nick of the bird. Means somehow they have been they could not become a disaster because of timely control of the situation. So there are many such events. Yeah.
Okay, I really appreciate that, Dr. Sushil, not only for this conference, but the team you are part of and the global rating, which is you're a major player. I really appreciate the excellent experience of global perspective. I thank you very much. And with your permission, I will go to the next speaker.
Yeah, thank you.
I would like, thank you very much from India.
Yeah,
hi, say hi.
It's a pleasure to attend. Yeah, thank you.
Okay, I would like to go now. Before we go to Germany, I would like, because we have some requests from the audience, to go over the schedule of the day, because there was a bit slight of change. So I would like, thank you very much. So I would just say, and please, all the audience all over the world, please, you can take a picture in your telephone about this 4 slides that I will talk about. So you can see this is almost the exact time of the conference today. So please take your camera out and take a picture of what you see right now on the screen. So we have block A, we started. We're gonna have one more lecture from Germany, our dear colleague and expert of radioactive materials, and then specifically battery in space. So this is going to conclude the next slide. The next lecture from Germany of Dr. Daniel Freis will conclude this block A. Now we'll go to block B, so you can all please take a picture. Please go to the next slides. Thank you. This is block B. I'll give you a few seconds so you can take a picture of this slide. Block B will take us to the afternoon side. Okay. We'll talk about Aaron Friedman, which are Steele and Gelberg, which will go on in a few minutes. And then we have this a very interesting panel, and we're going to expose kind of the Israeli ambiguity. Does or does it not still holding to do what have been done for 70 years or so? So please, next slide. And this is block C. You can all also take a picture of it so you know what the time is, what lectures are more specific, important to you. And please go to the last slide. Okay, this is block D. This is going to conclude the evening. And we're going to see, we have Roy Laufer, which is an expert. And one back, please. One back, please. Okay, so this is block D. You can take a picture of it. Thank you very much. I would like to introduce our friend, our dear colleague friend from Germany, Dr. Daniel Freis. Dr. Daniel Freis is a leader of European Commission, DJ DONT Research Center, JRC, Nuclear Safety and Security. The lecture will go over the safety of nuclear fuel and atomic batteries in space. It's not a new thing of nuclear battery in space, because, you know, like submarine, they can go for a few months and sometimes year on the same fuel. And we have the same problem with energy in space. So Dr. Daniel Freis, which I have to say we met in Europe in a visit in a laboratory that deals with nuclear waste, is also important. And I'm sure that Dr. Joshua Sokol will explain to us in the future, and will break another myth like the dirty bomb. So about nuclear waste is not a problem as people or as institute unfortunately present to the world. So Dr. Daniel Freis, please take the floor.
One of the most fascinating fields of science is the exploration of space. This can be done from Earth using telescopes, or we can send spacecraft. But in this case, we need a reliable source of power. Hello and welcome to my talk, Safety of Radioisotope Power Sources for Space. Slide 2. My name is Daniel Freis. I'm a nuclear engineer and I work as a scientific officer for the European Commission's Joint Research Center in Karlsruhe, Germany. The JRC is the scientific service of the European Commission, and we support the development of EU policies with independent evidence. The JRC employs about 3,000 scientists at 5 research sites, which are located in Belgium, Germany, Italy, the Netherlands, and Spain. Slide 3. JRC Karlsruhe is located at the site of the Karlsruhe Institute of Technology, and our mission is to carry out the nuclear work program funded by Euratom. Our directorate contributes to the scientific foundation for the protection of the European citizens against risks associated with radioactive material and provides scientific support for the community policies related to nuclear energy. We also contribute to an effective safety and safeguard system for the nuclear fuel cycle. The JRC supports the ESA research program on radioisotope power systems based on americium-241. Here, we focus on the development of methods to stabilize the americium and to establish a safe and reliable pelletizing process. To enable these activities, JRC Karlsruhe has a unique infrastructure for handling, characterization of highly radioactive materials. For instance, the so-called minor actinide laboratory, which consists of shielded glove boxes and remote handling tools to protect the workers from the radioactive radiation, and allows working with significant amounts of minor actinides. Slide 4. There are different options to supply a space probe with energy. First, there is solar energy, and if the mission target is close enough to the sun, this is probably the best and most efficient way to generate power. However, the intensity of the solar radiation is decreasing with the square of the distance from the sun, and this means that for all destinations in the outer solar system, the surface area of the solar cells would become unpractically large. The slide indicates the solar distance of circa 3.5 astronomical units of the ESA space probe Rosetta when it met with the comet 67P Churyumov-Gerasimenko in 2014. It can be seen that the solar radiation has decreased to circa 8% of the solar radiation at Earth orbit, and really large solar arrays of 64 square meters were required. This is also roughly the limit of practical applications. Another option are chemical energy sources, but such as liquid fuels or batteries, but their energy densities are usually too low to provide enough power for longer time periods. Nuclear energy sources have much higher power densities, and essentially all missions which go beyond the orbit of Jupiter require some sort of nuclear power. This is also the reason why ESA has defined radioisotope power systems as a key enabling technology for future European activities in space. Slide 5. The next slide shows the application range of different energy sources as a function of mission time and required power level. Nuclear power systems are divided into fission reactors and radioisotope power systems, RPS, which utilize the decay heat of a radioisotope to provide heat and electricity. Nuclear power systems are needed for all missions where a continuous power supply for a longer time period is needed, and where the distance to the sun is becoming too large, or where operation in the shadow of planetary bodies is required. In the following, we will speak only about radioisotope power systems and not about fission reactors. Slide 6. Radioisotope power systems have a number of advantages compared to other energy sources in space. They are compact, long-lived, reliable and robust, resistant against cosmic radiation, independent of sunlight, maintenance-free, and they have a high energy density. RPS have been used in space missions since the early 1960s by the United States, Russia, and recently also by China. The first launch of a RPS was 1961 by the US Navy on board the Transit 4A navigational satellite, and RPS were then used on many of the most spectacular missions in space history. The picture shows a SNAP 27 radioisotope thermoelectric generator used to power specific scientific instruments on the moon. Slide 7. There are two types of radioisotope power systems: heat to electricity conversion systems to supply onboard devices with electricity, and radioisotope heater units, RHU, which are only used to keep sensitive electronics at a minimum temperature during operation in the coldness of space. Heat to electricity conversion systems can be classified into dynamic and static systems. The dynamic systems employ moving parts and use a thermodynamic cycle to convert heat into electricity. Dynamic systems have the highest conversion efficiencies, but till today, they have not been proven to be reliable enough to support long-lasting space missions. The static conversion systems are called radioisotope thermoelectric generators, RTG, and they are composed of a stack of radioisotope heat sources inside an insulating casing. The heat is transferred to the outside via an array of thermocouples, thereby generating electricity. Finally, the heat is dissipated into space by thermal radiation by a number of fins. The picture on the left side shows an example of an RTG, the US multi-mission RTG, and the picture on the right shows the US lightweight radioisotope heater unit. Slide 8. RTG have no moving parts and are therefore extremely reliable. They are based on the Seebeck effect, where thermocouples made of two dissimilar materials generate electricity when they are connected in a circuit, and a temperature gradient is applied. Thermoelectric conversion is not very efficient, and practical RTG systems show typical power conversion systems of up to 7%. However, if they are operated at low temperatures, they are very reliable, show low degradation, and can provide power over many decades. Because of the importance of reliable and maintenance-free systems for automated space probes, relatively low conversion efficiencies are usually accepted. Slide 9. The most important design criterion for any space nuclear power system is safety. If an RPS is employed on a space application, it must comply with Resolution 4768 of the United Nations General Assembly, which states that the design of the RPS shall ensure that radioactive material does not cause a significant contamination of the biosphere. The accident conditions relevant to space systems are uniquely challenging. Potentially, the RPS has to survive a blast shock wave, followed by a fireball, impacting fragments, re-entry heating, and ground impact at high velocity, and all of these potentially in series. The picture on the left side shows an Antares rocket at NASA's Wallops Flight Facility exploding a few seconds after liftoff. Slide 10. There are a number of credible events to be considered in the safety analysis, and some of them are listed here. Especially the so-called swing-by or gravity assist maneuvers, where the relative speed and gravity of a planet are used to accelerate the spacecraft, constitute a risk and can lead to a re-entry accident. The graphics on the right side shows the trajectory of the spacecraft Rosetta, which performed 3 Earth swing-by maneuvers before it reached the comet 67P. Slide 11. The first RPS used metallic plutonium and were designed to burn up into fine particles, which would then disperse into the atmosphere in case of an accident. However, modern radioisotope power sources follow a strict containment philosophy and are designed to meet the highest safety standards. The fuel is encapsulated in a cladding of a high refractory material, like iridium or platinum rhodium, which can safely contain the radioactivity under all credible circumstances. The cladding is surrounded by thermal insulation, which is usually made of pyrolytic graphite and protects the cladding from high temperatures. Finally, the thermal insulation is surrounded by an aeroshell made of carbon-carbon composite, which provides additional protection against explosions or high-velocity impacts. Slide 12. There are many criteria for the selection of a suitable radioisotope. For instance, it should have a long half-life and a high isotopic power. The radiation should be low and there should be a compound which is chemically stable. The material should be compatible with the encapsulation materials and it should resist high temperatures. In case of an accident, it should not disperse into small particles and it should have a low solubility in the environment and the human body. The specific power correlates inversely to the half-life, which means that a compromise has to be found between specific power and durability. And the selection of a suitable radioisotope always depends on the application. Alpha emitters are usually preferred over beta emitters because the alpha decay does not generate Bremsstrahlung when stopped in the surrounding beta. Slide 13. The following slide shows a selection of potential radioisotopes, which were considered to be used for RPS. So far, mostly plutonium-238 was used as power-providing radioisotope due to its high power density, its long half-life, its chemically stability as oxide, and its low neutron and soft gamma emissions, which require no shielding. In a few cases, plutonium-210 was employed by the former Soviet Union, and americium-241 was selected by ESA for future European power systems. Slide 14. Another important criterion is the availability of the radioisotope and the effort which is needed to produce it. Plutonium-238 is produced by neutron irradiation of neptunium-237 and subsequent chemical separation. This process requires dedicated facility and is extremely costly. Currently, there is a global shortage of plutonium-238, and the USA are the only country with a significant program for its production. Europe does not have facilities which are suited for plutonium-238 production. Americium-241 is generated by the decay of plutonium-241 and can be separated from existing stocks of civil plutonium in France and the United Kingdom by chemical extraction. This is the reason why ESA has selected americium-241 as power-providing isotope. Slide 15. The next slide shows a comparison between plutonium-238 and americium-241. While americium-241 is easier to produce, it has some disadvantages compared to plutonium-238, such as a low power density and slightly higher radiation levels. In addition, the oxide shows chemical instability at high temperatures, and the experience with americium-241 is limited. Its relatively long half-life of 433 years can be seen as an advantage, since it would allow long missions with very low decrease in power generation, especially when the thermoelectric materials are operated at low temperatures. Slide 16. Unfortunately, the americium-oxygen system shows a complex behavior. The cubic dioxide, americium AmO2, loses oxygen at high temperatures and in the vacuum of space. This leads then to an increase in volume and finally to conversion into the hexagonal sesquioxide, Am2O3. The sesqui oxide, on the other side, is prone to oxidation and converts easily into AMO2 in air, even at room temperature. In both cases, dimensional changes are induced, which can cause the disintegration of the pellets. The diagram on the right side shows the different phases of the americium oxygen system, and the red arrows indicate the described phase changes which cause the disintegration. There are several options to overcome this issue. In principle, one could operate with AMO2 at very low temperatures and avoid the oxygen loss, but this would lead to very inefficient systems. Another option would be to find an alternative compound which shows sufficient high density and stability, and JRC is investigating this option. The third option is to stabilize the oxide in its cubic form. Slide 17. The stabilization of AMO2 was achieved by addition of circa 12% of uranium. In this way, it was possible to stabilize the cubic phase and to sinter a number of disks and pellets, including 2 prototype pellets in the dimensions of the US lightweight radioisotope unit and a larger disk representative for a future European RHU. Due to the absence of phase changes, the stabilized material showed a good sintering behavior, and it was possible to sinter a number of disks and pellets with good quality and without cracking. Slide 18. After sintering, oxidation testing was performed and the material proved stable up to 1000 degrees Celsius, as can be seen on the left side. This result represents a significant improvement with respect to safety of the material against radioactive material dispersion in case of accidental conditions. In addition, the swelling behavior was assessed and no macroscopic swelling was observed. Crystallographic swelling occurred due to the self-irradiation, but saturated after circa 60 days at circa 0.4 volume% increase. Overall, the pellet showed good stability under self-irradiation conditions. Slide 19. In order to meet safety requirements and to safely ship the RPS to the assembly site, qualified welding of the capsules is required. The encapsulation has to be performed in a nuclear installation, and it has to be ensured that the fueled clads are free of external contamination. In order to test the feasibility of our welding equipment and to gain experience in the welding of platinum-rhodium, 2 types of safety encapsulation were constructed and welding tests were performed. The capsules were welded using established tungsten inert gas welding. Non-destructive as well as destructive weld examinations were performed and showed good results. Thank you for your attention.
By the way, the email is full of questions and really appreciate that. We have to pick a few of them and I'll talk about in a minute. It's not only a global conference, but also with your professionalism, we're going out of space. So thank you for this, Daniel. Dr. Daniel, can you hear me? Okay, they will bring Dr. Daniel.
Yes, I can hear you.
Okay, thank you very much. If they can bring you, we have Dr. Daniel. Thank you very much for your enlightening presentation. And I would like to bring a question from Mr. Pierre from France in Paris, and he's asking: today it looks like there's no energy problem in the world. So if we have a battery that can go to space, is there or there is not a limit of energy once we go on space? Did you hear my question, Dr. Freis?
Yes. Well, I understand the question like this, that I think once you have the radioisotope power sources in space, you ask for the limit of the energy supply with respect to time and I guess power level. So with respect to time, I have to say that the limit is given by the half-life of the radioisotope, but more important is actually the degradation of the thermoelectric materials. So I think the most popular example for a space probe, which was sent in 1977 and is still operating, is the Voyager 1 and Voyager 2 space probes. So you can see that they are fueled with plutonium-238, actually, with a half-life of about 88 years. And you can see that they are still operating after more than 40 years of mission time. regarding the limit of power levels. If you have radioisotope heat source, you have normally power levels of up to a few hundred watts electric. So that is not something to supply a huge starship with it, but more for research for space probes.
Thank you. I really appreciate that, Dr. Freis. Thank you very much. And I forgot to say, but you're a major member of the Nuclear Forum. So thank you for presenting Germany. And please keep exploring space and teach us about it. So thank you very much, Dr. Freis. I would like to invite for a few comments, Dr. Stilian Gelberg. Please take the floor.
Thank you, Ori. Thank you, Daniel, for your inspiring presentation. When speaking about radioisotope power supply, one can have to mention the micro nuclear reactors. I think that this is the future of the nuclear reactors. They are small reactors, the size of a refrigerator. You can move from one place to another. They can provide something like 20 megawatt, something it's enough for 50,000 houses. And there are already more than 50 companies working in this field. And I am quite sure that in the next year in London, we'll speak much more about this micronuclear reactor. And this is the future of the energy. Thank you.
Thank you very much, Professor Stilian, for this information. And it is important because it's really the future of the nuclear as a small, medium reactor. And we all know that the United States and many other countries today, in 2021, in a few months from today, there are more than 50 patents all over the world. For example, Lockheed Martin and other companies that are applying for patent in the small, medium reactor. And the point is to take a truck, not too big of a truck, to take it in the middle of the desert and to supply electricity to more than 100,000 citizens. So they do not need to be connected to an electrical grid, but to get a power of a city of 100,000, the same as the base, and hopefully good things and not bad. I would like to remind you two things before we go to the break. First of all, we have this email. So if you can put the email on the okay. So thank you. Okay, you see the World Nuclear Forum, so you can keep us questions and discuss about information that we can take. And can you please put the slide of the break? We're going to take a break of 10 minutes right now, and we'll come back after the break to go on to number 2. Thank you to Block B. Thank you very much.